The first section of the section chair is the Dr. Gorgon of Logic. Please give a warm applause and that's welcome.
Okay, hi, can you hear me?
Yeah, it's very clear.
Okay, great. So welcome everyone. Welcome to the first session of QCrypt 2022. It's an invited speaker session. And I'm very excited to welcome Claude Crepeau, who will tell us about experimental relativistic zero knowledge. So before we start, let me just tell you a little bit about the format. So if you have questions during the talk, please use the Q&A box on Zoom and drop your question in there. I will then decide if it makes more sense to ask your question during the talk or to hold it off to the end and read it out to Claude. And then at the very end, when the Q&A session actually starts, you're welcome to also raise your hand and I can unmute you, or you can put your question into Q&A. Okay, so without further ado, let's hear from Claude. Welcome, Claude, and please go ahead.
Thank you very much. I hope you hear me well.
We do.
Okay, so it's a real pleasure to be here. I'm very flattered that I was invited as an invited speaker to lecture to QCrypt. And my presentation today is going to be experimental relativistic zero knowledge proofs. And so let me start by introducing you to my co-authors. Pouria Alikani, Nicolas Brunner, Sébastien Designol, Raphaël Ullmann, Wei-Xu Shi, Nan Yang, and Hugo Zbinden. Those two in pink pictures were from my research group, and the rest of the gray pictures are co-authors from University of Geneva. So imagine a situation where you're traveling abroad and you're trying to withdraw cash from an ATM, and you put your card in the ATM, and then suddenly you're asked for your PIN number. Now we all realize, as cryptographers, we all realize this is a very weak system because we're about to give away the identification information that would allow someone to replicate our identification to a machine that we have no clue whether it's real or fake. So if you interact with a machine that you have never seen before, you have no reason to trust whoever owns the machine. You actually know nothing about that. So as an approach to give better solutions to this situation, Goldwasser, Micali, and Rakoff in 1985 introduced the notion of zero-knowledge proofs. Zero-knowledge proofs are mechanism for a prover, here on the left, to demonstrate to a verifier, here on the right, the membership of a string W to a language L. So what we wish is that when the string W is actually in L, upon interacting with between the prover and verifier, the verifier should end up being convinced that the string is actually in L. So this is the completeness condition, and it says that the probability for the verifier to accept a string W when it is in L should be nearly 1 upon a proper conversation with the prover, whereas in the case where W is not in L, it should be almost never the case that the verifier will accept, and this regardless of the behavior of the prover. So even if the prover is dishonest, if the prover uses all its power and ability to try to convince the verifier that W is in L, it will not be possible for the prover to convince the verifier except with a very tiny probability. So the verifier rejects with probability nearly 1. Now soundness, as I just described, is a property protecting an honest verifier from a dishonest prover. Now the other component, the first component of my title, which is zero knowledge, is a property protecting an honest prover from a dishonest verifier. And that brings us back to our example of the teller machine. In the teller machine example, the verifier may be dishonest and may be trying to steal the identity of the prover. Now, I will not go into much details of what zero knowledge is during this talk because it's a somewhat fancy definition, but for the rest of this talk, we'll stick to a basic intuition that when a proof is zero knowledge, the proof that's provided by the prover to the verifier should not be replicatable by the verifier to a third party in such a way that he can use it to pretend to be the prover. Now, throughout this talk, I'm going to use considerably the tree coloring problem. I'm going to use the tree coloring problem in particular for maps. So this is also known as the graph tree coloring problem. It's a situation where you're given a bunch of regions, here represented by birds, connected to each other. And the problem of tree coloring is to assign a color to each region in such a way that any two neighboring regions must be of different colors. Now, obviously, the map with these five birds here is tree colorable, and you can see in the head of the prover a tree coloring that works. Now, indeed, the problem I'm describing is a graph problem. And in general, we consider the problem of tree coloring of graphs. But for the rest of this talk, to keep it simpler, I'm going to keep it with maps, which is more visual. Also, in an example of an actual demonstration of identity, we would use a much larger graph map, something like this. And in order to demonstrate his identity, the prover would have to demonstrate knowledge of a tree coloring of this map. So you can imagine that in a zero knowledge system, every user has a public map that's associated to his identity. And the prover demonstrates that he is the person with this identity by showing in zero knowledge that the map is tree colorable, and moreover that he knows a tree coloring. But for the rest of the talk, I'm going to stick to this small example so that we can see what's going on. Now, a very simple way of achieving completeness and soundness is for the prover just to provide the coloring to the verifier. Now, if the verifier obtains such a coloring, then it's very easy for the verifier to check that the coloring actually satisfies the tree colorability constraint, meaning that any two neighbors, any two regions that are touching each other must be of different colors. Now, if we did that, then it would be trivial for the intermediate region. Can I request that you turn your mics off? Thank you. So definitely, if we do as I just described, it will be transferable, and that's precisely what we're trying to avoid. Now, there's a famous result that you probably all heard of by Goldreich, Micali, Vigderson in '86, in which they found a mechanism in a zero knowledge proof for tree colorability. The protocol is as follows. It uses what we call commitments. Commitments are a procedure that I will describe later in our context, which in a first step, the commit step, allows the prover to make public a value that will later be revealed to the verifier in the second phase, the unveil phase. During the first phase, after the commit step, the value inside the safe is unknown to the verifier but is uniquely determined so that at a later point, when unveiled, the value that's revealed will be the content of the safe at an earlier time. It's not possible for the prover to change his mind about the content of the safe when it's made public. So the protocol is the following. Instead of revealing the colors to the verifier, the prover is going to commit to the colors, and is going to do that in a region by region. So he's going to make available the commitments of the colors of the birds in such a way that the verifier cannot see them. However, the verifier is going to be allowed to request for a pair of neighboring regions, in this example, region 2 and 3. And upon that request, the prover will unveil the content of those two regions and show the verifier that those two birds were of different colors. Now, however, if we want to get a satisfying soundness, we're going to have to repeat this protocol many times so that we can detect that the prover, if the prover doesn't know a tree coloring of the map, we want to be able to detect that. And so in order to do this, we're going to have to repeat many times, and each time see that the two chosen neighboring regions are of different colors. So in the second example, the region 02 can be chosen, and then the verifier will see that the two regions are of different colors. And yet the third example will show these two colors. Now, if we keep repeating like that, ultimately the verifier will obtain the colors of all the graph and will be able to repeat that to a third party, which is precisely what we're trying to avoid. So they introduced an extra trick to make sure that what is seen by the verifier cannot be used with a third party. The trick is to use randomization of the colors. So instead of reusing the same coloring each time, the coloring is replaced each time by a random one. It's random in the sense that the three colors, blue, yellow, red, are randomly reassigned. So in this example, we're going to reassign blue is going to be yellow, yellow is going to be red, and red is going to be blue. So that instead of using the original coloring, this randomized coloring is used instead. It's all recommitted to the verifier, and then the verifier can choose a pair of neighboring regions, as in the previous example. And so in this case, he would see blue and yellow instead of red and blue, as in the original. And so if you re-randomize each time before you commit and unveil, then what the verifier is going to see is just a bunch of colors that are pairwise distinct when you look at two neighboring regions, but there's no accumulation of information because of the randomization. The randomization is such that what the verifier will actually see are repeatedly just two random colors assigned to two neighboring birds. Even if you ask for the same birds many times in a row, you would see the same two birds with all possible pairs of colors appearing on them. Now, this is not transferable, and in particular, it's not transferable even if the verifier is dishonest. Now, the property of zero knowledge is somewhat more involved in not being transferable, but for the rest of this talk, I'll just stick with non-transferability as a notion of zero knowledge, and I'm sure you can all go to the literature to find out more about zero knowledge. But in order to implement the protocol of GMW, how do you implement commitments? And traditionally, in the single prover, single verifier model, This has been done using computational assumptions. And that's precisely what this talk is trying to avoid. We're trying to avoid using computational assumptions. We would like to get commitments that are perfectly hiding, meaning that the content of the safe is completely unavailable to the receiver, to the verifier, and the value inside the safe is uniquely determined throughout the protocol so that the prover cannot change his mind and have more than one value possibly open in the unveil phase. Now, in a setup where the prover and the verifier are arbitrarily powerful computationally, it's long known that achieving commitments is impossible. And it's an information theoretical argument if the content of the safe is perfectly hidden from the verifier, then somehow it must be that the value is not uniquely defined and that the prover can change his mind. And if the prover cannot change his mind, then there must be a way for the verifier to tell what the unique value is. So this is sort of a short proof structure for how one proves that these two properties cannot be satisfied at once. So because of this fact, the idea of multi-prover interactive proofs was later brought in. This was by Benor, Goldwasser, Killian, and Vigderson, who introduced the idea of having more than one prover. So the provers at the bottom here are allowed to prepare for questioning about the string W, and the verifier is going to talk to both of them and quiz them about facts regarding W that should convince him or not that W belongs to a certain language. So we're going to request a completeness property, just like in the single prover case. And what we request is that upon interacting with the two provers regarding string W, we wish that the verifier will accept that W is in the language with probability nearly 1. Of course, when W is actually in the language. And for soundness, we wish that whatever the provers do, whatever strategy they agree on, whatever randomness they may share, and whatever discussions they have with the prover, with the verifier regarding string W, they should not be able to get him to accept the string W as a member of the language. So we wish that the probability after interacting with potentially dishonest provers of accepting the string is very small. That's, of course, when W is not in language. However, this is under the special condition that the two provers cannot talk to each other. Now, what does it mean, and what did the authors mean when they said that the provers cannot talk to each other? Now, one candidate answer to this question was given by Killian a couple years after they introduced the notion. Killian suggested that instead of having two provers and one verifier, we should use two provers and two verifiers, provers and verifiers being close to each other, whereas the two pairs are far remote from each other. You can imagine at two ends of a table, at the two ends of a city, or on planet Earth and planet Mars, for instance. Now, this is what we call relativistic multi-prover interactive proof. And the reason why it's called relativistic is because in this setup, we use the limit of the speed of light, which limits the speed at which information can be transferred between, in particular, the provers in this case. we use the distance between those in order to make sure that for a short lap of time, it's impossible for them to talk to each other because they have to have a conversation with their local prover at in such a short time that it's physically impossible for them to have communicated with their partner within the short lap of time that's available for them. Now, the question of what it means not to communicate may seem obvious, but indeed it's very far from obvious. John Bell in the 1960s wrote an amazing paper on the Einstein-Podolsky-Rosen paradox, in which he discussed the notion that quantum mechanics appears to give a stronger notion than classical mechanics of what it means to not talk to each other. Now, Bell introduced two frameworks, one being the framework of locality, in which he defines what he considered classical mechanics meant when it said two people cannot talk to each other. In locality, if two parties receive inputs A and B and have to output X and Y as a function of the inputs, locality is going to be something of this flavor where the left party can use only his own input in order to compute its output, and the rightmost party will only use his own input in order to compute its output. If on top of that the function is deterministic, then we say that this is local deterministic strategies, allowing the parties to compute their output from their input. Now, locality is a little bit more general than this. Locality allows the two parties to also share randomness. So they have coin tosses that they pre-share, and they each own a copy of these coin tosses, and they're allowed to compute their output X as a combination of their input A on the left, the coin tosses. So X is going to be some distribution with input A, and the distribution is generated by the randomness of the coins that are shared. And the same thing on the right-hand side, the output Y is computed from the input B, as well as the joint coin tosses that they share. Now, what's particular about this situation is that it's forbidden for the leftmost party to use B in its computation of its output, and it's forbidden for the rightmost party to use A in the computation of its output. They're only using their own local input. Now, in the time before John Bell, it was commonly agreed upon among physicists that the notion of not talking to each other corresponded to this model. Now, what Bell realized is that the notion of quantum entanglement introduced by Einstein-Podolsky-Rosen has this property that it allows to achieve correlations XY given AB that are not possible using local correlations only. Now, without going into details, the quantum non-local correlations are obtained by sharing a quantum state psi and using POVMs on each side in order to produce the output from the input. Now, what Bell realized is that what he called local hidden variable models, which is the blue circle, correspond to those correlations that are possible using the first local model. Now, this is a very tiny subset of all possible correlations, which we obtain by signaling. So if you allow the two parties to communicate or signal to each other, then any possible correlation can be achieved by them. Now, what Bell realized is that quantum non-locality is going to be a little bit bigger than local hidden variable correlations, but is still not achieving signaling. So it remains impossible for people to signal using quantum non-locality. Now, in modern days, we realize that it's possible to extend these notions. We can extend the notion of signaling to the notion of left signaling and right signaling, which are subclasses of the general signaling correlations. The left signaling correlations can only signal from left to right, and the right signaling correlations can only signal from right to left. Now, at the exact intersection of these two classes lays what we now call the no signaling correlations. The no signaling correlations is a generalization of quantum non-locality. It's the set of all correlations that do not have enough power to communicate. You cannot use these correlations to send information from one side to the other, yet this is all the possible correlations with this property. Now, it's known today that this set of correlations contain more than quantum non-locality. So an example of an element in the no signaling subset is the PR box for Popescu-Roerlich, which was introduced as an example, as an extreme example that cannot be achieved by quantum non-locality, and which has a remarkable property that anything in two-party no signaling can be achieved from using repeatedly this box and local operations. Now, the bottom line of this section is that when we analyze interactive proofs, and in the multi-prover case, we have to say precisely what is the model that the provers can have access to. Can they use local hidden variable? Can they use quantum non-locality, or can they use no signaling? Now, as a good paranoid cryptographer, I would like to make the weakest assumption. I would like to make an assumption that the provers can use any no signaling strategy, even if we don't know how to physically achieve them, because we have a physical model for local hidden variable and for quantum non-locality, but we do not have any physical operation that allows to do no signaling correlations outside of quantum non-locality as yet. So we don't know that for now, but to be on the safe side, we would like to do the non-local case, the no signaling case for the provers. However, at this point in time, we absolutely know not a single one zero-knowledge protocol that resists to no signaling provers. And that will be one of my open questions at the end of the talk. Can we design some zero-knowledge interactive proofs with multi-prover that resist no signaling in general, even if we don't know how to do no signaling in our physical reality? So let me go back to the problem that I started in the beginning. I want to go back and tell you about our protocol. And so we're going to consider the protocol of Goldreich, Mikhaili, Wigderson in the context of Benor, Goldwasser, Killian, and Wigderson, which is in the context of multi-provers. So the protocol of GMW is to commit to every color of the map, and then to unveil two of them. Now, if we follow these guidelines, do we get a quantum sound solution? If we apply directly the GMW protocol in the context of the original paper who introduced multi-prover? And unfortunately, the answer is no. It's not going to be quantum sound because the described protocol is not known to resist quantum adversaries. It's not known to resist to quantum provers that use entanglement in their proofs in order to correlate their answers in the proofs. Now, on top of that, is this protocol practical? And I would like to argue that such a protocol is not really practical. It's not practical for a reason that I will explain in a few minutes using a second example, which is a recent protocol of Chailloux and Leverrier. So in 2017, Chailloux and Leverrier introduced an alternate protocol, again used on commitments, but instead of using tricolorability, they use the problem of Hamiltonian cycles. And because of the special structure of Hamiltonian cycle, they were able to demonstrate that their protocol, using similar commitments to the previous situation, have the property of being quantum sound. And this is a remarkable result. However, it's still not very practical. And let me explain in details a little bit more why it's not so practical. You see, the problem is, if you locate the prover-verifier pairs at a certain distance from each other, and you do the commitment of all the edges of the graph in their case, it's going to take a certain amount of time for the commitments to happen here on the left. And on the right, when you want to unveil, you have to make sure that the unveiling starts after the commitment has been done on the left. And so this diagonal means that fact. And you have to make sure that the unveiling ends in such a way that the leftmost party cannot have obtained information from the rightmost party. So the space-time diagram here shows two constraints that depend on how much time you need in order to commit and how much time you need in order to unveil. Now, unfortunately, if you make the instances bigger, the space between the prover-verifier pairs will have to increase because the time to commit is going to get bigger. Now, a back-of-the-envelope calculation using the figures of the Chailloux-Leverrier paper and using very, very fast communication equipment. So a year ago, I found this headline that there now exists a 319 terabits per second communication device somewhere in Japan. Even if you could afford to buy this super equipment, it would still be the case that 200 kilometers would be necessary between the provers in order to do the commitments and make sure that from beginning to end of the commitment, no information can go to the other prover or come from the other prover. So in their protocol, if you use reasonable sizes, you're going to have to use distance that are very large. Now, what we are after is a protocol that will allow very short distances between provers and verifiers. Ultimately, we would like to be able to do that, say, with a smart card, something like this. A smart card, maybe two smart cards, say at a meter distance, something of that magnitude, so that the proofs can be done in zero knowledge with a teller machine, a special device teller machine that has two slots for two cards about a meter away from each other. Now, the major difference between their solution and ours is that the amount of communication that has to be done in each round of the proof is cubic in the size of the instance. for the protocol of Chailloux-Leverrier. And it's something similar for the protocol of Benor, Goldwasser, Killian-Wigderson. Now, ours, on the other hand, is only logarithmic in the size of the input instance. So it's logarithmic in the number of nodes of the graph or the number of regions of the map that we're using. Now, some of you may know about the PCP theorem, and logarithmic communication may sound familiar to you. Now, there's a paper by Dwork, Feige, Killian, Naor, and Safra, which uses the PCP theorem to achieve something similar to what we're doing. Now, the PCP theorem says something about the number of randomness you need to share, about the size, the number of places that you're going to look in a proof to convince oneself. But it also says something about the size of the proof that the provers will have to keep track of throughout the protocol. And in the case of the PCP theorem, this would be very large. Some large polynomial, so maybe we're going to use graphs with 1,000 edges. Maybe they would have to use 10 to the 20 ingredients in their proof, because the exponent, although it's polynomial, it's a fixed exponent, would grow the size of the input tremendously. So that too is not practical. So let me explain our protocol. What we managed to do is to use very few commitments. So let me explain. Let's say this is the graph, and we label the bird 0, 1, 2, 3, 4 like this. So our protocol is going to be as follows. One verifier is going to request this prover with two neighbors, as in the GMW protocol. But instead of giving away the colors, as in the GMW protocol, the prover is going to commit to those two colors to the verifier. Now, at the other end, we're going to do something similar at the other end. And the other verifier will request two neighboring regions, 0, 2 in this example, and the prover will also commit to those two regions to his prover. Now notice that I use two colors for commitments, the black commitments and the white commitments. And I'm going to define this notion in more detail in a second. But basically what's important is that there are two versions of every commitment. And it has a remarkable property that if you obtain both the white and black commitment at a given region, it will allow you to see the color. So let me tell you how we achieve such commitments. We achieve such commitments by first agreeing on a numerical value assigned to each color. So let's say red is 0, yellow is 1, and blue is 2. So the two provers agree on these. Now, in order to commit to the colors of the regions, they agree on randomized values, traits, such that the sum of two traits give you the color of the region. Now, we use what we call the unveil via commit principle. The unveil via commit principle is that if you obtain both a black commitment and a white commitment of the same region, then you're able to obtain the color. So let me tell you precisely what the protocol is. One verifier asks its prover for the labels of two regions. It identifies two regions, and it uses bit B to specify if he wants a black or a white commitment. And the prover responds with the two labels corresponding to these two regions, And so these corresponds to the commitment in black or white of that region. And we do something similar with the other pair of prover, with an I prime, J prime that's chosen in some way related to I and J, and B prime, which is chosen randomly. Now, two cases can occur here. If the two B and B prime are the same, and if there's a common node K to both positions, to both provers, then it should be that they answer the same. The two provers are expected to use a common table, and if they have a common table, they will respond with the same answer. Now, on the other hand, if we ask with distinct Bs, then we are able to actually see the color. So the protocol will alternate between cases like this one, where we're just going to check that if you ask the same commitments for the same node with the same color, that you get the same answer. This is consistency check. Or situation where we're going to be able to obtain two regions with both black and white commitments, and from this obtain the colors of the two regions. Now, for soundness, we have that, of course, for honest provers, this is giving us exactly what we're after. For dishonest provers, they can use arbitrary tables. They don't even have to use the same table, and they don't even have to use a table that's assigning a labeling to each node, but it can be done for each pair. Now, what's important is that we were able to demonstrate that the soundness error is going to be something like 1 minus 1 over a constant times the number of edges of the graph. And if you repeat a number of iterations, which is something like 5 times the number of edge times a constant k, then the soundness error becomes exponentially small in this case. As for the zero knowledge part, we refer back to the GMW protocol, and we show that depending on how the dishonest verifiers choose the edges, they will either see the color of two neighboring regions, the color of a single region, or the color of zero region. So let me say a little bit about our experimental setup. Our experimental setup was constructed at the back of the physics department at Geneva University. It involves FPGAs for the provers and verifiers, and PC to manage communication between the two verifiers. The two verifiers use an optical link of about 60 meters to synchronize their questions appropriately. And at a distance of 60 meters, we were able to achieve a demonstration of the protocol. Now I'm running out of time, so let me move on a little bit further. So what we were able to demonstrate is that at a distance of 60 meters, we were able to implement the protocol with two local prover verifier pairs, and it ran for about 1 second. So in 1 second, we were able to repeat the protocol enough times so that we achieved a very small 2 to the minus 128 security level, and this using graphs of 588 nodes and 1,097 edges. So this is an eloquent demonstration that it is feasible. Now, this demonstration was done using off-the-shelf equipment, and this off-the-shelf equipment was enough to achieve 60 meters, and we have back of the envelope calculations showing that with special tailored pieces of equipment, we could bring this same protocol to about a scale of a meter. And so it's actually feasible to do these zero knowledge proofs on such short distances if you use the right protocols. Let me jump to my conclusions. So what we have achieved in the local case of the local provers, is we've demonstrated the feasibility of relativistic zero knowledge for tricolorability in about a second with a reasonable cryptographic level of security. The implementation we used was based on off-the-shelf equipment, and we can do even better using sophisticated equipment. In the entangled case, we have demonstrated that it's feasible using essentially the same equipment, but the running time is too big. I skipped over this discussion, but the problem is that when we change from local provers to entangled provers, we have to use a larger number of rounds to actually achieve the same security level. And currently this running time is too big, unfortunately. So let me end with a few open questions. In the entangled prover case, we would like to find a better soundness error bound so that the number of iterations reduces significantly and become practical. So what we were able to do in about 1 second in the local case would take very many hours, even with very sophisticated communication equipment. And so we're looking for better soundness errors. We don't have a lower bound saying that it's necessary to do all these rounds, but we don't have a good enough upper bound to reduce this number significantly. And there's also a technicality that what we proved is demonstrating that if a graph is not recolorable, then it will not be possible for the prover to convince the verifier. Now, actually, what we want to show is that if the graph is tricolorable, but the prover doesn't know a tricoloring, then he will not be able to convince the verifier either. And in the local case, this is done already, but in the quantum case, we're still missing some subtleties here. And finally, in the no signaling case, if we want to be on the paranoid side and go for no signaling as a model of no communication, then we would like to show some zero knowledge protocol that's sound against no signaling provers. And right now, the only such protocols that we have are the trivial examples like graph isomorphism or quadratic residues that are natural examples that are zero knowledge without any assumption. So let me end here. It's been a pleasure to introduce you to my recent research. If you would like to read more about it, this work was published in the Nature journal on the 4th of November, 2021. This is the logo of my research group at McGill. Thank you very much for your attention.
Thank you, Claude, for the wonderful talk. So if you have any questions, please drop them in the Q&A box. In the meantime, let me ask a question or two
Sure.
in the minute or two we have left. So I'm curious, based on your open questions at the end, whether you've thought about parallel repetition theorems, either for your protocol or for a similar protocol. Is such a thing even possible in the relativistic setting?
Yes. The trouble with parallel repetition is that we do have a general parallel repetition theorem by Ran-Raz in the local case. In the quantum case, there's no such thing yet as a fully parallel repetition scenario. There are some possibilities out there that help to do parallel repetitions, but all our efforts right now so far to improve the protocol through parallel repetition has not succeeded in more efficient protocols in the end. And similarly, in the no signaling case, we don't have a general parallel repetition theorem either. So it's definitely a direction to consider, but it has not been powerful enough right now to help us. And so we still favor the sequential repetition instead of parallel one.
So maybe continuing with that, I mean, are there any things that you can, because of the relativistic setting, completely rule out? Like, for example, you know, in the sort of single, in certain settings, in the sort of single prover, single verifier setting, we can even do like non-interactive proofs. Is there, you know, can you prove a theorem that says that in the relativistic setting there isn't, you know, there isn't even such a thing?
I honestly don't know. I'm sorry.
Okay.
I think it's a good question, but I really have no idea.
Okay, great. We're really out of time now, so so please, everyone, join me in thanking Claude in whatever way you can, and thanks again, Claude, for a wonderful talk.
Thank you very much. It's been a great pleasure. Looking forward to seeing you at some other occasion.
Thanks to the Dr. Jorgen leading, and thanks to the Dr. Claude's remarkable speech. And now we have a 15 minutes coffee break. Please take a break and join the networking in the discussion lounge on the Event X. Please come back at 11 o'clock Taipei time to participate in the second section of the conference. Thank you.